Hello, you're welcome back. All right, so we will continue from where we stop. All right, so we have already discussed the electrical conductivity of semiconductors. Okay, so here we're going to be looking at the types of semiconductors. All right, starting. Okay, we have two types of semiconductors basically. Okay, we have the intrinsic semiconductor and the extrinsic semiconductor. Okay. So I will start with the intrinsic semiconductor. What are intrinsic semiconductors? Okay, so of course, intrinsic semiconductors are semiconductors in their pure form. Okay, they are in their pure form. So that means they are not actually mixed or they are not combined with any impurities. So the semiconductor we discussed earlier on, okay, are actually that of intrinsic semiconductor, a semiconductor in its pure form. All right. Now, example of an intrinsic semiconductor in its pure form, we have germanium, and of course we have silicon. Okay, mind you, one chemical characteristics, okay, of intrinsic semiconductors is that their atoms, okay, they have four valence electron, okay, and of course you know that 4 is actually midway between from midway between 0 and 8. Okay, so invariably if you go to periodic table you can actually uh, group them as metalloids, neither metal nor non-metal. Okay, but we are not discussing chemistry here, so always take note that for every semiconductor, okay, you always have every semiconductor have 4 valence electron, that is 4 electron in their atmosphere shell. That's one thing you should know about them. Okay, so basically that's information about the pure semiconductor. They are in their pure form. All right, so we've talked about their conductivity. We say that their conductivity is only temperature dependent. Okay, without heat, without them being heated, they cannot conduct, and we have actually generated the formula for their conductivity. We say that is given as Ni. Okay, the concentration or density of the charge carriers multiplied by the electronic charge, bracket open, mobility of the electron plus the mobility of the hole. So I still hope that you can still remember this formula. This is very, very important. As we now discuss the next type of semiconductor, which is extrinsic semiconductor. Now, extrinsic semiconductors are, as the name implies, they are impure semiconductor. They are in their impure form. Okay, why are they impure? Why? Because they are basically doped with impurity. They are doped. The word doped is like a chemical combination, so they are chemically combined with impurities. So impurities are simply, they are still atoms, okay, but they are atoms of other elements. So impurities are atoms, but they are atoms of other elements. All right. Now it happened that this extrinsic semiconductor, okay, is further divided into two types. All right. So extrinsic semiconductor divided into two types. We have the N type. N type extrinsic semiconductor, and we have the P type. And we are going to discuss them one after the other and okay, of course, illustrate how they are being formed. The word N represents negative, while the word P represents positive, okay? So we have negative type semiconductor and positive type semiconductor. So depending on the impurity that we use in doping an extrinsic semiconductor, all right? In doping an intrinsic semiconductor, we can either arrive at N-type or P-type. So let's start with the N-type semiconductor, all right? N-type semiconductor. How do we actually achieve an N-type semiconductor? It's very easy. Okay, we achieve that by actually doping an intrinsic, a pure form of semiconductor. We dope it with elements that have pentavalent at all, simply pentavalent atoms. Pentavalent. Of course, you know what that pentavalent means, okay? Pentavalent are atoms that have 5 valence electron in the atmosphere. Atoms that have element whose atoms have 5 valence electron in the atmosphere. For example, we have phosphorus. Okay, I think arsenic is also one. Arsenic. So this particular element, the atoms of this element have 5 valence electron. Now let's see what is the implication. Already we know that an intrinsic semiconductor, a pure semiconductor, have 4 valence electron. I'm now doping it with a pentavalent atom, okay, 5 valence electron. And this combination is, we call it covalent, okay, combination or covalent bonding. So in covalent bonding, the two, substance or the two atoms actually share electron. This one will contribute 4, this one will contribute 4. So it's called that this one have 5 already, so it has an excess. So that it contribute 4 and this one contribute 4, they will evolve in that bond formation. Then the excess, there's going to be an excess. Okay? So this is going to produce XX1 electron that is not involved in bonding. One excess electron, okay? So this one excess electron now is very much free with a very high energy, okay, to conduct electricity. So it's very much free to be at the conduction band. Why? Because it is not bounded at the valence, okay? It is not bounded to the atom. So what's if an electron is not bounded to the atom, invariably that electron can actually conduct electricity, okay? So if we are now being asked for N-type semiconductor, what is the charge carrier, or what are the charge carrier? Okay, now N-type semiconductors, as you can see, have electron as charge carrier, but that doesn't mean that the semiconductor doesn't have hole. Remember, it's still a semiconductor, all right? There are still some temperature. Anytime there's a temperature, you get some hole, but very in a small amount. So the majority charge carrier, or the major thing that contributes to the conductivity of N-type semiconductor, is simply this SS electron. So if you are not being asked in exam, okay, so the majority charge carrier of N-type semiconductor majority charge carrier, okay, is simply electron. And we all know that electron is negatively charged, okay? So negatively charged, that is what we call this semiconductor N-type. Why? Because the charge carrier are electrons, and they are the one that they are negatively charged. But there's still gonna be minority charge carriers. So the order, which of course is whole, minority charge carrier, because what? The whole, which we know is positively charged. But it doesn't make much of an import, okay, as I call it minority. It's only the whole that is actually generated, the whole generated thermally, okay? It's generated based on the temperature of the semiconductor. But the major one is the electron, which we know is negatively charged. Okay, so please take note of that. So now let's now go to conductivity, the formula for conductivity. So if I want to express the formula for conductivity, okay, conductivity of N-type. So if I want to express the formula for the conductivity of N-type semiconductor, what will I ask myself? I'll ask myself, what is the major charge carrier? That's electron, okay? Whole here is minority, so I can neglect the whole. So what you have here is only the electron. So anything I have to do with whole is actually negligible. I can neglect it. All right, so let's now go to the formula. So the conductivity of n-type semiconductor is going to be giving us n, and of course electron density, because it's only electron. The only charge carrier is electron, okay? So I would have said the charge carrier density, but since we know it's only electron, I will only call it electron density, okay? Electron density of the n-type. Using this n here simply means that I'm considering the n-type. If it was p, I would have used p as a subscript. Then of course multiply by the electronic charge, okay? Then of course multiply by the mobility of just the electron. This is one way of expressing it. Okay, so write this formula because we are going to apply it. Now, this is one way of expressing. Then that way of expressing it, I can express it based on, okay, the based on what actually brought about this electron, electron. What actually brought this electron? Okay, this SS electron. This SS electron is not coming from this intrinsic semiconductor. It's coming from this pentavalent atom. Is this pentavalent atom that donated this SS electron, okay? So I call it the donor atom. So to every atom, that means one atom of this pentavalent element will always donate one SS electron. So depending on the number of this pentavalent element, I will have equal number of what electrons. So if I am not express the concentration based on the number of electrons, I can also express the concentration based on the number or the concentration based on the number of pentavalent atom. Okay, because there is no electron without a pentavalent atom. All right, and there is, so I can actually write my formula again. Okay, using this ND EUE. Okay, so what does this ND represent? This ND represent the density or the concentration of the donor atom. That pentavalent atom is the donor atom because it's the one that donated the SS electron that is used for this conductivity. Okay, so I can, this question number 2, so I can write that down. Okay, NN, that is electron density. Electron density of the n-type. Then ND, okay, is a donor, okay, the donor atom density. Donor atom density or even concentration, okay? So please take note of that as we now discuss the other type, the p-type semiconductor. Okay, so discussing the p-type semiconductor. How is a p-type semiconductor formed? Now, a p-type semiconductor is formed when I dope, or when a pure form of semiconductor is doped with, this time around, trivalent atom. Trivalent atom, all right? Example, aluminium. Aluminium have 4 valence electron, even boron, okay? 4 valence electron. And what's the implication of that? Okay, so the implication of this is that I'm combining 4 valence electron, okay, atom with 4 valence electron with atom with just 3 valence electron, So it discovered that now this atom that I'm using to dope now is deficit. Its electron is not complete, okay, and that's a vacant electron. Just one vacant electron or one deficit electron. Remember what we always refer to as deficit electron, okay? It's always in electronics, we call it what? Hole. A point where there is no electron, okay, is regarded as a hole and is positively charged. So this combination now will leave us with one positively charged hole. One positively charged hole. So that way now we can now conclude that for a p-type semiconductor, the charge carrier, the majority, please, is, we always call it majority because there are minority, okay? So that doesn't mean that there are not other charge carrier, but others are minority. So for p-type semiconductor, the majority charge carrier is equal to the whole, which of course is positively charged. So no wonder it is actually called p-type, positive charge semiconductor. All right. So if majority is the whole, then the minority, you always have minority, okay, due to heat or temperature, and that minority is the thermally generated electron. But if we are expressing our conductivity, okay, we'll always neglect the minority, then we'll consider the majority. So now let's look at that expression. Let's evaluate the expression. Okay, now I want to evaluate the expression for the conductivity. Conductivity of p-type semiconductor. Okay, let's see how it works. So conductivity of p-type, you know very well that all we have, the charge carrier is just a hole. Okay, so that's gonna give me, that is pp, hole concentration. That's what I mean of p-type. Of course, multiplied by electronic charge, then mobility of the hole. Okay, so pp, hole, okay, density, hole density of p-type, Okay, of course, you know what the UH represents, mobility of the hole. Then you know also that we can also express this form in another way by considering where this hole is coming from. This hole is coming from, remember where it's coming from? That atom, that trivalent atom, okay? The one that have a deficit of electron. So that one, I don't call it donor. That one is acceptor. It doesn't donate it, it only accepts, okay? So I can also express conductivity as the concentration of the acceptor atom multiplied by the electronic charge, then multiplied by the mobility of the hole. So Na, concentration of acceptor atom. All right, so I hope that is well understood. Please take note of the formula. It's really very, very important. Okay, so now for us to summarize this, having discussed the two types of intrinsic semiconductor, N-type, and P-type, and they are gotten by doping a pure semiconductor with either a pentavalent or a trivalent. Now, we are going to look at a particular law, known as law of mass action. Law of mass action. Okay? Look at the law. The law states that the product of electron hole density, of a semiconductor is always constant. Let me say that again. This product of electron hole density of a semiconductor before and after doping is always constant. So that means the product of electron of a pure semiconductor and its hole of the same pure semiconductor will always be equal to the product when it is being doped. Let's say when it is doped with N, okay? It's going to be equal to the product of the electron density multiplied by the product of the hole density. That is if the doping is for N type. The same thing happened, okay? Ni, electron hole density of the intrinsic semiconductor, okay? The product of the electron hole density of the intrinsic semiconductor is also going to be equal to the product of electron hole density, okay, of the p-type semiconductor. So before and after doping, that product will always be equal. So please take note of that. That is the law of mass action. So just find somewhere and write it down. Then, of course, you know very well for an intrinsic semiconductor, both electron and hole, they are equal, of course, in pairs. Okay, electron density is equal to hole density. We know that already for an intrinsic. Okay, so that simply means that I can write this formula now as, since this is equal to this, that is going to be Ni times Ni. That's going to be Ni square. So Ni square is equal to Nn Pn. Or I can simply say that Ni square is equal to Np then Pp. Okay, so we are going to apply all this formula and this law, okay? We are going to apply it in the next video. All right, see you in the next video. Thank you very much.